Section 9.7 is linear, quadratic, and exponential models. I can choose a linear, quadratic, or exponential model for data. Big ideas for this section. Linear, quadratic, or exponential functions can be used to model various sets of data. Graphing and testing data can show which type of function best models the data. If we look here at the take note, talks about some different types of functions that we've dealt with so far. Linear functions have the form y equals mx plus b. First degree functions there, and they form a line, straight line. You can use a straight edge to connect them. Quadratic, second degree. Remember, these are our parabolas. And there's pictures of the graphs with the take note. Exponential has our variable in the exponent. These look kind of like these, okay? Remember, they have an asymptote they're never going to cross. They're going to go really small to really big, or really big to really small, okay? So, straight line, symmetric parabola, or exponential, where it grows really, really fast and gets really, really small really, really fast. In example 1, we're going to graph each set of points and figure out which model is most appropriate for the set. So, our first set, I have 1, 3. I have 0, 0. I have negative 3, 3. I have negative 1, negative 1. And I have negative 2, 0. Okay, if I were to connect these, it looks like it would be a parabola. Okay, it's symmetric, both sides, and it goes up like a U-shaped graph like our parabola. So this one here is quadratic. Second one, 0, 2. Negative 1, 4. 1, 1. And 2.5. If we look here, guys, maybe this is a parabola, but it doesn't quite fit the parabola. Maybe we just don't have the other side. But if we look here, guys, our parabola doesn't go up by the same amount every time. And here it does. Here it goes up, it doubles. It goes from half to 1, from 1 to 2, from 2 to 4. So since it doubles here, guys, we have a common ratio. Remember, that means it's exponential. So this would look something kind of like this. Okay, exponential. And again, maybe it would have been quadratic and we just didn't have the other side of our other branch. Maybe this point was our vertex. But it still didn't quite fit that over 1, up 1, over 2, up 4 kind of thing that we've talked about with quadratics. Here, our change in between every time was the same. It didn't have to double, it could have been whatever, but because it was the same, as a ratio, as something that was being multiplied, that meant it was exponential. And see here, negative 1, negative 2, 0, negative 1, 1, 0, and 3, 2. Here, if I took my straight edge, I could connect all those points into a line. Okay, that means, that this is linear. Okay, connect all of them with a line, so it's linear. Now, feel free to pause here and give this a try if you'd like. I have 0, 0, 1, 1, -1, -1/2, and 2, 3. If we look here, we only have one side again. And we're going up by a common ratio. Here, I go up by 1/2. Here I go up by 1. Here I go up by 2, which means my next point would probably be here, up by 4. This is exponential. I don't have both sides of my parabola, okay? And I have that common ratio. We're multiplying by the same amount every time. Exponential. For B, -2, 11. -1, 5. 0, 3. And 1, 5. So here, because this is going to make that U-shaped graph, and even though I don't have this point here that I would need for it to be symmetric, these points are, which means here I'm going to have quadratic function. We can also look at the data and determine what type of function best models the data numerically. So when the x values in a set of data pairs have a common difference, which means they go up by the same amount, so like -2, -1, 0, 1, 2, or 0, 2, 4, 6, 8. Okay, when there's the same difference between our x values, we compare the changes in our y values. So if our outputs, or our y's, have a common difference, which means we add or subtract the same number, the points represent a linear function. If the outputs have a common ratio, which means we multiply by the same number, then we have an exponential function. And that makes sense, guys, because here if we're adding the same number every time, for example, we represent that repeated addition by multiplication. Here, if we have a common ratio, let's say we're multiplying by the same value every time, okay, we represent that with an exponent. Okay, we represent repeated multiplication with an exponent. We represent repeated addition with multiplication. If the outputs do not have a common difference or a common ratio, we evaluate this second difference, third difference, and so on. Which means, let's say, we're going to do an example like this one in a minute, but if they don't match up first, see if we can get them to match. The number of differences that we've taken matches the exponent of the function. So if the second differences are common, the function represents a quadratic function. If the fourth ones were common, for example, it would be x to the 4th power. Okay. Which type of function best models the data? Use differences or ratios. So in A here, I'm going to try and figure out, first of all, that my x's go up by 1 every time. I have a common ratio there. They're consecutive. So then I check my y's. To go from 9 to 5, I subtract 4. 5 to 1, I subtract 4. 1 to 3, subtract 4. -3 to -7, I also subtract 4. So since I have a common difference here, this is linear. In B, I go from 0 to -0.25. I can't do that by multiplying, so I'm going to have to subtract -0.25. Then I subtract 0.75. I subtract 1.25, and I subtract 1.75. Okay, those don't match. We can't try multiplication because I can't go from 0 to a number. So it's not exponential and it's not linear. So let's check our next differences. Here I subtract 0.5. Here I subtract 0.5. Here I subtract 0.5. So since our second differences, here's our first differences, Here's our second differences, match up, and they're all the same. My second difference means it's quadratic. Now, which type of function best models the ordered pairs? Use differences or ratios. So to go from -1 to 0 to 1 to 2 to 3, I have consecutive values. My differences are the same there. So now I can compare my outputs. I have 0.5 in my y column, 1, 2, and 4, and 8. Sorry. So if I look here, I can either add 0.5, but when I go to 1 to 2, I add 1. Those are different. So that's not the path that I'm going to use. Okay, I'm going to check to see if multiplication will work. And again, maybe we have to find our second differences, but we should at least check multiplication. Half to 1 means I multiplied by 2. 1 to 2 means I multiplied by 2. 2 to 4 times 2, and 4 to 8 times 2. So since I multiplied every time, I represent repeated multiplication with exponents. So this is an exponential function. Real-world data rarely falls exactly into a linear, exponential, or quadratic model. So what we're going to do, however, is pick the best possible model. So the data in the table on page 591 gives the value of a used car over time. What type of function best models the data? And then we're going to write an equation to model the data. So if we look here at our data, we're going to have to figure out the change between these. Here I found our common differences, and I did that by taking 11,065 minus 12,575. Okay, and then all the way down the line. So I found our common differences. Here, those don't look like they're going to match, so not linear. It also doesn't look like our second differences are going to match. Here, for example, we dropped 300. Here, we don't. So second differences aren't going to match either. So let's check and see if we can multiply to get there. So here I found my common ratio, and just like when we talked about before when we did sequences, I find my common ratio by taking my second value over my first value. Here I get approximately 0.88. My second set, I get approximately 0.88. My third set, I get approximately 0.87. And my last set, I get approximately 0.88. So again, guys, real-world data doesn't always give us exactly the same amount, but we're pretty close here, okay? So I'm going to say that my common ratio is 0.88, and this is exponential because I have a common ratio. Now, we're going to write that equation. Remember our standard form, a times b to the x power. A is our initial amount, and that's at time 0. So here, 12,575 times b is my common ratio, 0.88 raised to the x power. So we said this is an exponential model, and there is our equation. Now, the table on the bottom of page 591 shows the annual income of a small theater company. What type of function best models the data? Write an equation to model the data. So the first thing I'm going to check, guys, is common differences and see if they match. Here my data is pretty close. And remember, I take my second number minus my first number to get my values. 2 of them are 480. 2 of them are very, very close to 480. So since I can add the same amount approximately each time, I'm going to say this is a linear model. Remember, that means y equals mx plus b. Our change every time is our slope. Our initial amount is our b. So y equals, I'm going to use 480 here because that's kind of the average of all of those and the one that appears twice, times x plus where we started, 18,254. Linear, quadratic, or exponential functions can be used to model various sets of data, and graphing and testing data can show which type of function best models the data. That's all for section 9.7.